This video is part 2 of the solution set for problem number 71 from section 12.1 in the Calculus Stewart edited book, that's 6th edition, and it's dealing with the Fibonacci sequence. So in the first video we looked at how we could determine the Fibonacci sequence based off of the question he posed with rabbits, and in the second part of the video we looked at this ratio of a sub n, which was f sub n plus 1 divided by f sub n, and we went ahead and proved this statement of a relationship between these a's with different subsets. So now our final piece here in part 2 is assuming that a sub n is convergent to find its limit. So what that's saying is the following. When we say that a sub n is convergent, it means that a sub n is going to be progressing towards a particular value. Now again, note that a sub n is a ratio. It's a ratio of one of your sequence values in your Fibonacci sequence divided by its previous value. So when we say that it's convergent, we're saying that for this a sub n, as your n is approaching infinity, meaning as you continue through these many months with your rabbits, or whether it's anything related to the Fibonacci sequence, as your n is approaching infinity, this ratio, this a sub n ratio, is going to approach a value of L, is what we'll say. So as we continue through month 3, month 30, month 300, 3000, and we're looking at the sequence value of 3000 plus 1 divided by the sequence value at n equals 3000, we're going to be moving towards a particular value of L. Which means, when you think about it, that the other forms of that same ratio should also be approaching the value of L. Because a sub n, again, is just a way of expressing this ratio between two subsequent months. And if you look, when we had a sub n minus 1, it's 2 subsequent months, and the same thing with n minus 2, 2 subsequent months. So as we're heading towards infinity, these three essentially become one and the same. So we can say, well, if we're going to assume that the limit as n approaches infinity of n sub 1, or a sub n, is L, then we can say that the limit as n approaches infinity of a sub n minus 1, oops, let me clean that up there, that the limit as n approaches infinity of a sub n minus 1 is also L, just as the limit as n approaches infinity of a sub n minus 2, because again, these are all describing the same type of ratio, they just moved the months that they were looking at. And it ultimately doesn't matter when we're going to infinity, it should also equal L. So let's take this information and, let's apply it to this piece. They had us to show that this a sub n minus 1 equals 1 plus 1 divided by a sub n minus 2. This will be very helpful in helping us to determine what this limit actually is. So if we apply the limit as n approaches infinity to both sides of this equation, you'd have the following. You'd have the limit as n is approaching infinity of a sub n minus 1, which would equal the limit of the entire right-hand side. So n as it approaches infinity of 1 plus 1 over a sub n minus 2. And this is supposed to be a minus there. There we go. Okay. So if we apply the limit to both sides, well, we have definitions for these different limit pieces, so let's apply them. So this left-hand side just becomes L. And if we continue on the right-hand side, well, the limit of 1 as n approaches infinity, it's not dependent upon n at all, so it's still going to be 1. And we have 1 divided by a sub n minus 2. Well, again, this one is just like our 1 over here. It's not affected by this limit, so it's still going to be just simply a 1. But our term in the denominator is going to become L. Why? Because it's part of what we just said right over here. The limit as n approaches infinity of a sub n minus 2 equals L. So there's the replacement. So at this point we have L equals 1 plus 1 divided by L. So it looks like we need to get all these L's on one side if we're going to figure out what the limit value actually is. So let's see if I can scoot this down some. There we go. May need to extend this page. There we are. So I'm going to take this over here. So we have L equals 1 plus 1 divided by L. There it is. And in order to get all these L's on one side, it seems like we're going to have to break this L out of its denominator. So to do that, let's multiply the whole thing through by L, so both sides. So now I have L squared equals L plus 1. So now we don't have to worry about denominators anymore. Everyone is on the same level. And L squared, L1, I'm sensing some sort of quadratic thing coming on. So let's move everybody onto the same side. So you have L squared minus L minus 1 equals 0. Yep, it looks like we're going to have to do some sort of quadratic setup to determine the value of L. Now, we're not going to worry about trying to figure out a particular factoring pattern. Let's go straight to the quadratic formula and knock this out. So if you remember, we'd say that in this case it's L instead of an X. It's going to be the opposite of B, so opposite of -1, which is 1. And we'd say plus or minus the square root of B squared, so that'd be -1 squared, minus 4 times A times C, so it'd be 4 times 1 times -1. There we go. And then that's all divided by 2A. So in this case, it'd be 2 times 1. So let's see if we can clean this up a bit. So we have the 1, that still stays the same. And we have plus or minus. -1 squared is just going to be a 1. So we've got that. And then we have -4 essentially times 1 times -1. So we really have 1 plus 4. So it's a positive 4 in there. So 1 plus 4, that's square root, divided by 2 times 1, which is 2. A little bit more cleanup, and I think we'll have it. We have 1 plus or minus the square root of, 1 plus 4 is 5, divided by 2. Now the question becomes, are we going to have a negative or a positive value? Well, for that part, let's actually take a look at what's happening in our sequence. We find that as we go through our sequence, we were increasing in value. So let's see. Too far down. Here we go. So if we were to take a look at our sequence, we had, for starters, let's see, it was 2, 4, 6, 10, 16, 26, and we knew that the sequence said that we would need to add the 2 previous terms to find the next term. So 16 plus 26, that gives us 42. 26 plus 42, that gives us 68. 42 plus 68 gives us 110. So let's see if we can find anything using this set of values to determine whether or not we want the plus or the minus version of this limit. So so when we have our a sub n, remember we said a sub n was going to be our next term divided by our current term. So in the case of here, we have the 2 and the 4. Well, 4 divided by 2 gives us a 2. Write this in green. There we go. And then 6 divided by 4, well, that's, let's see, 1.5 if I'm not mistaken. So that's 1.5. Then 10 divided by 6 gives us 1 and 4/6, so it's about 1.66, 1.667. And then 16 divided by 10 is 1 and 6/10, then we're looking at 1.6. And let's see, for this next one, I'm going to have to use a calculator, but as we continue on, we'll see that these values start to progress towards a bit of a 1.61, 1.62, okay? And as a result, if we check the value that we'd have from 1 minus the square root of 5 divided by 2, and then compare that to 1 plus 5 divided by the square root of 2, we'll find that of these two options, we actually want the second one. We want this plus. Because as we continue through our sequence and we're looking at this ratio of a sub n, it's moving towards this value of 1 plus the square root of 5 divided by 2, which is about 1.60, 1.61. And so that answers the end of problem number 71. Again, you can take this set of values, plop it into Excel if you'd like, continue on the sequence, and create another column looking at ratios if you're interested. Again, Fibonacci sequence is one of my absolute favorites because it shows up so much in nature. And it's just a really, really neat number sequence. So if you have any questions on how we set up any of these different parts and how we were able to evaluate this limit and the sequences, just let me know. And there we have it.